This study explores the effects of thermal modification on the flexural properties, transverse fracture energy, and hardness of western hemlock, a wood species increasingly used in construction due to its desirable mechanical properties and aesthetic appeal. The thermal modification process involves subjecting wood to high temperatures, typically between 160 and 240 degrees Celsius, without oxygen, resulting in improvements in durability and resistance to decay. Previous studies have shown that thermal modification can lead to varying outcomes depending on factors such as wood species, treatment temperature, and duration. For instance, Haku et al. Reported that thermal modification of beech wood enhanced its dimensional stability, hardness, and decay resistance. Similarly, Yildiz et al. Found that thermally modified spruce wood exhibited improved dimensional stability and fungal decay resistance. In terms of mechanical properties, Pleshberger et al. Observed a decrease in the tensile strength parallel to the grain in softwoods like radiata pine, Scots pine, and Norway spruce after heat treatment. However, they also noted an increase in compressive strength parallel to the fibers and a significant reduction in impact strength. The current research focuses on the effects of thermal modification at 167 degrees Celsius on the flexural properties, transverse fracture energy, and hardness of western hemlock. Flexure tests on specimens with longitudinal and transverse grains revealed that thermal modification slightly improves the flexural modulus and strength, while reducing statistical variability compared to unmodified samples. However, fracture and Janka hardness tests showed a more pronounced brittleness in the thermally modified samples, with a 47% and 60% reduction in total modi fracture energy for radial, longitudinal and tangential, longitudinal systems, respectively. The average Janka hardness in the tangential, radial, and transverse planes was also lower in the modified specimens, by 8.5%, 3.9%, and 9.4%, respectively. The findings suggest that thermal modification can significantly affect the fracturing behavior of western hemlock and its energy dissipation capabilities. These changes must be considered in design, as they influence the damage tolerance of this wood in the presence of stress concentrations, such as those induced in bolted joints and cutouts. Furthermore, the study's results are consistent with previous research on other wood species, highlighting the importance of understanding the specific effects of thermal modification on different types of wood. This study aims to fill a knowledge gap in the field of wood engineering by investigating the effects of thermal modification on the mechanical behavior of western hemlock, particularly its fracture energy and hardness. The research focuses on the potential benefits of using thermally modified coastal western hemlock for structural applications, such as cross-laminated timber, CLT, panels. A preliminary study by Norian and Avramidis, 2021, has shown that thermal modification can significantly improve the dimensional stability of western hemlock, leading to enhanced building envelope seal and consistent glue line thickness in CLT panels. The present article provides comprehensive guidelines for designing with thermally modified western hemlock, contributing to the development of rich databases for calibrating and validating computational design tools. It also serves as a reference for integrating an undervalued USBA-SED wood species into structural design standards and computational models. Advances in understanding the mechanical behavior of thermally modified wood could positively impact its use in mass timber elements like CLT. The sample material for this study was acquired from a small harvest of coastal western hemlock from the Macaw Reservation in Washington state. The forest is designated as a Site Class 3. Low productivity forest with an average age of 100 years. The wood was kiln-dried to a moisture content of 20% and then thermally modified at 180 degrees Celsius, 200 degrees Celsius, and 220 degrees Celsius for 2 hours. The thermal modification process involved heating the wood in a nitrogen atmosphere to prevent burning or discoloration. The mechanical properties of the thermally modified wood were evaluated through various tests, including 3-point bending, impact bending, and Brinell hardness tests. The results showed that thermal modification significantly improved the dimensional stability of western hemlock, enhancing its potential for use in CLT panels. However, the mechanical behavior was not significantly affected by the thermal treatment, suggesting that the wood's strength and stiffness remained relatively unchanged. The findings of this study have implications for the design and construction of CLT panels using thermally modified Western hemlock. The improved dimensional stability could lead to better building envelope seals and more consistent glue line thickness, ultimately enhancing the structural integrity and durability of the CLT panels. Furthermore, the study's results contribute to the development of rich databases for calibrating and validating computational design tools, paving the way for the integration of thermally modified Western hemlock into structural design standards and computational models. This study focuses on the thermal modification of Western hemlock wood, examining its effects on bending and fracture properties. The research utilizes a 55.88 cm diameter, 396 cm log obtained from a commercial timber harvest program in a forest with a mean annual air temperature of 8.89 degrees Celsius and a mean annual precipitation of 203.2304.8 cm. Two boards were cut tangentially from the middle section of the log's radius, with one board designated for longitudinal and transverse bending specimens and the other for single-edge notch bend (SENB) specimens. The boards underwent an accelerated drying regime in a Wisconsin oven for up to 4 days, with temperatures not exceeding 48.89 degrees Celsius. Moisture content measurements were taken daily, and the boards were removed from the drying regime once their moisture content dropped below 13%. Some cracking and shrinkage effects were observed, but they were minimal and did not affect the production of straight, crack-free samples. One length of each bending, SENB, and Janka hardness board was set aside and allowed to remain at ambient conditions until the time of individual specimen preparation, constituting the unmodified, samples. The other two lengths of bending and size effect boards were sent to Thermal Wood Technologies in Poulin, Montana for a thermal modification treatment. The wood underwent a standard production cycle with a 7.5-hour total run time, including a 3.5-hour temperature increase to 167.78 degrees Celsius, a 1.5-hour dwell at 167.78 degrees Celsius, and cooling to 70 degrees Celsius. The pressure profile is proprietary but designed to complement the thermal cycle and expedite the modification process. These boards constitute the thermally modified (TM) samples. Grain structure of TM and longitudinal bending specimens is shown in Figure 3, with loading direction down from the top of the image. Longitudinal and transverse bending specimens of and TM wood were prepared as per ASTM D143 for secondary method specimens. Boards were planned on a grizzly planer down to 25 mm thickness, then ripped parallel to the grain on a sawstop table saw, sampled from the edge farthest from the pith of the tree. They were run back through the planer at 25 mm to reduce dimensional variability from the table saw prior to being cut to length. Transverse specimens spanned the entire width of the board and were ripped perpendicular to the grain. All samples were cut to length on a DeWalt miter saw. Cross-sections of grain structure for and TM longitudinal bending samples are shown in Figure 3. 25 and TM samples were produced for each grain orientation. SENB specimens were prepared for fracture testing in a similar fashion to bending specimens, utilizing the planer to achieve more precise dimensions whenever possible. The study aims to investigate the effects of thermal modification on the bending and fracture properties of Western hemlock wood, providing insights into potential improvements in wood durability and performance. This study focuses on the mechanical behavior of Western hemlock wood, particularly examining the effects of thermal modification on its fracture properties. Two types of wood samples were used: untreated, and thermally modified, TM. The single-edge notch bending, SENB, test was employed to assess the fracture energy of these samples, with two configurations investigated: radial-longitudinal, RL, and tangential-longitudinal, TL. The SENB specimens were prepared with dimensions as outlined in Table 1, featuring a 0.254 mm wide edge notch cut using a hand saw. The RL system exhibited larger fracture energies and fracture process zones, FPZs, compared to the TL system, necessitating the testing of two sizes for the RL system to ensure size-independent fracture energy measurements. Conversely, only one size was tested for the TL system due to its reduced susceptibility to size effects. The wood blocks for Janka hardness testing were cut from the same log, displaying similar annual growth ring patterns and densities at equilibrium moisture content, EMC. Testing involved Flexure and SENB tests on a test resources 316 series UTM with a 22 kN load cell and a displacement rate of 5.08 mm per minute. Digital image correlation, DIC, was utilized to characterize the strain field and estimate the compliance of the fixture and machine, verifying the cross-head displacement measurements. The paper's primary focus is on the comparison of fracture properties between and TM Western Hemlock wood, with an emphasis on understanding how thermal modification impacts the wood's mechanical behavior. By employing the SENB test and DIC, this research aims to provide insights into the size effect on fracture energy and the influence of grain direction on fracture behavior. The results from these tests will contribute to a deeper understanding of the structural integrity and potential applications of thermally modified wood in construction and engineering. The research paper presents a comprehensive analysis of the mechanical properties of a novel wood-based composite material, focusing on its potential for sustainable construction. Pages 9 and 10 detail the experimental setup and methodologies used to evaluate the material's performance in various tests. Figure 6 illustrates the test setup for single-edge notch bending, SENB, and longitudinal, transverse bending tests, which utilized 10 mm and 30 mm rollers respectively. These tests aim to assess the material's resistance to crack propagation and bending strength under different loading conditions. Following the fracture tests, scanning electron microscopy, SEM, imaging was conducted on selected specimens to examine the fracture surfaces. A Phantom Pro X SEM with an electron beam voltage of 15 kV and chamber pressure of 60 pascals was employed. Images were captured 515 mm away from the crack tip and at least 1 mm away from the edges to avoid any damage caused during sample preparation. Additionally, Janka hardness tests were performed using a custom-made indenter machined to a diameter of 11.3 mm, adhering to ASTM D143 standards. The indenter was attached to a United SFM 300KN electromechanical series universal testing machine, and data was recorded via the United Datum 5i software. The specimens were loaded at a rate of 6.35 mm per minute until reaching a maximum penetration depth of 5.65 mm, which is half the diameter of the fixture. 6 hardness values were obtained from each of the 40 specimens, with 2 measurements taken from the tangential, radial, and transverse faces. Average hardness values were calculated for each face of each sample and then for each face of the 2 configurations. Figures 7 and 8 showcase the machined Janka hardness indenter and its placement on the specimen during testing. This setup allows for precise measurement of the material's hardness in different orientations, providing insights into its anisotropic behavior and potential applications in construction. In summary, the research employs a range of experimental techniques to evaluate the mechanical properties of the novel wood-based composite material. By examining its resistance to crack propagation, bending strength, and hardness in various orientations, the study aims to determine the material's suitability for sustainable construction projects. The detailed methodologies outlined in these pages demonstrate a rigorous approach to understanding the material's behavior under different loading conditions, shedding light on its potential as an alternative to traditional building materials. Results from longitudinal and transverse bending tests on thermally modified, TM, and unmodified, wood samples are presented. Longitudinal bending tests revealed that samples failed in tension, exhibiting simple and splintering tension failures, as well as cross-grain failures. In contrast, TM samples failed in a more brittle manner, with less deformation and crushing at the loading head. Figure 9 shows typical fracture surfaces of longitudinal flexure specimens. The modulus of rupture, MOR, and modulus of elasticity, MO, values were calculated from the maximum load and bending strain, respectively. TM wood exhibited 7% higher MO values and 5% higher MOR values compared to wood. However, these values varied from those reported in the Wood Handbook for Western Hemlock, potentially due to differences in grain structures, density, and forest characteristics. Transverse bending tests showed that both TM and samples failed in a brittle, fragile manner, with sudden and complete cleavage through the cross-section. The fracture surface was smooth following the grain. The Mohr and Mo values for transverse bending tests are presented in Table 2. TM wood exhibited lowered transverse strength and slightly lowered transverse stiffness compared to wood. The coefficient of variation, COV, values for longitudinal bending tests were consistent with a study on young-growth western hemlock, which reported lower Mohr and Mo values due to lack of tree maturity. The study's findings suggest that thermal modification affects the bending properties of wood, particularly in the longitudinal direction. The increased brittleness and reduced deformation of TM wood may be attributed to the thermal treatment process. However, the study also highlights the importance of considering the variability in wood properties, as reflected in the COV values. The results have implications for the use of thermally modified wood in structural applications, where bending properties are critical. This study focuses on the mechanical properties of thermally modified and unmodified western hemlock wood, specifically in terms of its modulus of rupture, Mohr, and fracture energy. The Mohr is a critical parameter that reflects the wood's resistance to bending forces and is influenced by grain orientation. The research reveals that the thermal modification process leads to a significant increase in Mohr for both longitudinal and transverse directions, with an increase of 5.2% and a decrease of 28%, respectively. The paper also explores the fracture energy of the material, which is a crucial parameter in understanding the wood's resistance to cracking. The single-edge notch bending, SENB, test was employed to characterize the fracture energy in both radial-longitudinal, RL, and tangential-longitudinal, TL, configurations. This approach allows for the estimation of both the initial fracture energy, GF, and the total fracture energy, GF, of the material. The initial fracture energy drives the failure in small samples where the fracture process zone, FPZ, cannot fully develop, while the total fracture energy represents the total energy dissipation per crack area down to complete failure and drives the behavior of very large notched structures for which the FPZ can develop fully prior to failure. The study utilizes the work of fracture method to estimate the fracture energy, which requires the measurement of the vertical load and vertical displacement. This approach overcomes difficulties related to the estimation of the fracture energy from the rate of the elastic potential or using the J-integral, especially in wood samples where a consistent grain orientation throughout the sample is challenging to achieve. The use of the work of fracture method simplifies the analysis and eliminates the need for a real digital twin of the sample, making it a more practical and efficient way to evaluate the fracture energy in wood. The results from the SENB tests show that the thermal modification process significantly affects the fracture energy in both configurations, with a higher initial fracture energy observed in the unmodified specimens compared to the thermally modified ones. However, the total fracture energy is higher in the thermally modified specimens, indicating that the thermal modification process enhances the wood's resistance to cracking in large structures. Overall, this study provides valuable insights into the effects of thermal modification on the mechanical properties of western hemlock wood, highlighting improvements in Mohr and fracture energy. These findings have implications for the use of thermally modified wood in structural applications, particularly where resistance to bending and cracking is crucial. The fracture behavior of quasibrittle materials, such as wood, is characterized by an initial and total fracture energy, which can be accurately determined only when the load softens down to zero. However, this is often challenging to achieve due to the limitations of testing machines. To address this, an exponential decay function, y equals a caret bx, is used to extrapolate the stress, where y represents the force, x represents the vertical displacement of the beam, and a and b are constants calibrated by fitting the lower portion of the softening load displacement diagram. Fracture tests on unmodified western hemlock wood exhibit similar crack propagation patterns for both radial-longitudinal (RL) and tangential-longitudinal (TL) systems, with the plane of crack propagation always orthogonal to the neutral axis of the sample. The fracture behavior is relatively brittle, with clean fracture surfaces. However, the fracture surface morphology differs between the two systems, with the RL specimen exhibiting damage in only one layer of vertical trachid cells, while the TL specimen exhibits damage in multiple layers, resulting in delamination and fracturing of ray cells. The load displacement curves for the RL system exhibit stable crack propagation with load softening, allowing for the estimation of both the initial and total fracture energies. The decay function fits the shifted curves well, enabling the extrapolation of the total fracture energy. In contrast, the larger size specimens exhibit a more brittle behavior, characterized by snapback instability, making it challenging to calculate the fracture energy. However, the results suggest that size effects on the fracture energy are minimal, and the fracture process zone, FPZ, can develop fairly well even for smaller specimen sizes. The research paper presents an analysis of the fracture behavior in unmodified and thermally modified wood samples, focusing on the radial-longitudinal, RL, and tangential-longitudinal, TL, systems. Page 17 illustrates the load as a function of vertical displacement for unmodified size 1 and size 2 samples of the RL system, with Figure 15 and Figure 16 respectively. The plots show the shifted load displacement curves with fitted extrapolation functions used to calculate the initial fracture energy and the total fracture energy. The RL system exhibited snapback instability with dynamic crack propagation, which hindered the calculation of the work of fracture for size 2 samples. In contrast, the TL system demonstrated stable crack propagation, despite its larger size compared to the RL systems. However, fewer valid tests were available due to the presence of knots. The fracture tests were very consistent, allowing for a full estimate of both the initial and total fracture energy for this system, as shown in Figure 17. A summary of the fracture energies measured for the two unmodified systems is presented in Table 3. The results indicate that both the initial and total fracture energies of the RL system are significantly larger than those of the TL system, consistent with similar tests on spruce wood. The results are extremely consistent, with the maximum coefficient of variation, COV, on the fracture energy being only 10.1%. Page 18 discusses the fracture tests of thermally modified Western hemlock, which exhibited similar behavior to the unmodified wood. In both the RL and TL systems, the plane of crack propagation was always orthogonal to the neutral axis of the sample, despite differences in mesostructures. The fracture behavior was generally brittle, with relatively clean fracture surfaces. Figures 18 and 19 display the max principal strain right before failure for the thermally modified wood samples, further illustrating the consistency of the fracture tests. In the context of the research on fracture mechanics in wood, the authors present a comparative analysis between radial-longitudinal, RL, and tangential-longitudinal, TL, systems. The study focuses on the strain fields, grain patterns, and fracture surfaces of thermally modified wood specimens. The RL system exhibits damage in only one layer of trachid cells, with ray cells being perpendicular to the crack propagation. This results in fracturing of the ray cells. In contrast, the TL system shows more extensive damage, involving about 23 layers of trachid cells, and delamination and fracturing of ray cells as they are in plane with the crack propagation. The load displacement curves for thermally modified size 1 and size 2 samples of the RL system are presented. These plots display stable crack propagation with load softening visible in the experimental data. The fitted extrapolation function is used to calculate the initial fracture energy and the total fracture energy. The figures provided illustrate the grain patterns and SEM images of the fracture surfaces for both the RL and TL specimens. The strain fields, as depicted in the figures, show similar patterns for both cases, with strain concentrations at the crack tip and at the grains. However, the fracture surface appears different, reflecting the distinct damage mechanisms observed in each system. The study highlights the importance of understanding the influence of thermal modification on the fracture behavior of wood, particularly in terms of its grain orientation and damage mechanisms. The results suggest that the TL system exhibits more extensive damage and different fracture mechanisms compared to the RL system. This research contributes to the development of new strategies for improving the fracture resistance of wood through thermal modification. Here is a combined summary of pages 21 and 22. Low displacement curves were obtained for thermally modified wood, enabling the characterization of both total and initial fracture energies in most tests. For the larger size, crack propagation was relatively stable, albeit with only 2 tests allowing full characterization of total fracture energy. The tangential-longitudinal (TL) system exhibited similar behavior to unmodified wood, with stable crack propagation in all tests and consistent load displacement curves. These curves allowed for accurate calculation of fracture energies, as shown in Figure 22, where the shifted load displacement curves with fitted extrapolation functions were used to calculate initial and total fracture energies. Table 4 presents a summary of the fracture energies for thermally modified wood, revealing that the radial-longitudinal (RL) system has a larger fracture energy compared to the TL system, consistent with unmodified wood. However, the values of fracture energies are significantly lower. A comparison between thermally modified and unmodified wood reveals that thermal modification leads to significant embrittlement in the RL system, with a 41% reduction in initial fracture energy and a 47% reduction in total fracture energy, as shown in Figure 23. Similarly, for the TL system, the reduction is even more dramatic, with a 52% decrease in initial fracture energy and a 60% decrease in total fracture energy, as depicted in Figure 24. These findings highlight the significant impact of thermal modification on the fracture properties of wood. The study investigated the impact of thermal modification on the mechanical properties of Western hemlock, focusing on longitudinal and transverse flexure, fracture energy, and hardness. In the longitudinal direction, thermal modification led to a 6.8% increase in modulus of elasticity, (Mo), and a 5.2% increase in modulus of rupture, (Mor). However, in the transverse direction, while Mo increased by 6.7%, the transverse Mor experienced a significant 28% drop. Fracture energy for both radial-longitudinal (RL) and tangential-longitudinal (TL) systems showed a substantial reduction due to thermal modification. For the RL system, initial and total fracture energies decreased by 41% and 47%, respectively. In the TL system, the initial and total fracture energies decreased by 52% and 60%, respectively. These findings are crucial for designing Western hemlock structures, as the reduction in fracture energy and Janka hardness induced by thermal modification must be considered for material damage tolerance and energy dissipation upon crushing. Ballistic performance is strongly correlated with these properties. Janka hardness tests revealed that average hardness values were reduced due to thermal modification, with a statistically significant decrease observed in the tangential and transverse wood planes. This decrease in surface hardness is consistent with previous research, which showed that surface hardness generally decreases with thermal modification, especially at higher temperatures. The results of this study underscore the importance of considering the effects of thermal modification on Western hemlock's mechanical properties, particularly in terms of its potential use in structural applications. The provided pages present a comprehensive list of references related to the thermal modification of wood, focusing on its effects on the material's properties, fracture mechanics, and size effect. The references span various fields, including materials science, wood science, and structural engineering. The cited works investigate the impact of thermal modification on wood's bending properties, strength, and toughness, as well as its relation to polymeric structural wood constituents. The effects of moisture on the bending properties of thermally modified wood are also explored. Furthermore, the references examine the characterization and analysis of torrefied wood, the critical role of degree of polymerization of cellulose in superstrong nanocellulose films, and the surface hardness of thermally treated woods. The list of references also delves into the investigation of the reasons for fungal durability of heat-treated beech wood, the thermal modification of wood as a review of chemical changes and hygroscopicity, and the high temperature and chemical effects on wood stability. Additionally, the works cited explore the strengthening and toughening of hierarchical materials, the effect of thickness on the fracturing behavior of discontinuous fiber composite structures, and the effect of platelet size on the fracturing behavior and size effect of discontinuous fiber composite structures. Other key topics covered in the references include the bending strength and toughness of heat-treated wood, the structural changes of oak wood main components caused by thermal modification, and the multiscale analysis and experimental validation of crack initiation in quasi-isotropic laminates. The list also encompasses studies on the physical and mechanical properties of young-growth Douglasfir and western hemlock, the effect of thermal modification on mechanical properties of Canadian white birch, and the effects of fire-retardant chemicals on the bending properties of wood at elevated temperatures. Overall, the references provide a thorough overview of the existing research on the thermal modification of wood, highlighting its effects on the material's properties, fracture mechanics, and size effect, as well as its potential applications in various fields. The thermal modification of wood has been extensively studied, with various researchers investigating its effects on the material's properties. Norian, 2018, examined the thermal modification of western hemlock, while Pleschberger et al. 2014 analyzed the changes in fracturing and coloring of solid spruce and ash wood after thermal modification. Chow and Salviato, 2019, conducted a size effect study on the strength and cohesive behavior of thermoset polymers at the microscale. The literature review highlights the importance of understanding the mechanical properties of thermally modified wood. Reinprecht, 2016, discussed the deterioration, protection, and maintenance of wood, while Rylam, 1985, proposed a method for determining the fracture energy of mortar and concrete using three-point bend tests on notched beams. Rochik et al. 2020, investigated the moisture-dependent strength properties of thermally modified Fraxinus excelsior wood in compression. The review also covers the physical and mechanical properties of thermally modified wood, including the work of Goverchin et al. 2009, on ash Fraxinus excelsior and Salviato et al. 2016, on intralaminar energy dissipation and size effect in two-dimensional textile composites. Sandberg and Kuttner, 2016, discussed recent developments in thermally modified timber in Europe and North America. The literature review also touches on the color and chemical changes of thermally modified wood, as studied by Sikora et al. 2018, on spruce and oak wood. Song et al. 2019, examined the structure-property relationships of hydrothermally treated western hemlock. The U.S. Department of Agriculture, 2010, provided a comprehensive handbook on wood as an engineering material, while Wang and Wang, 1999, investigated the effects of moisture content and specific gravity on static bending properties. The review concludes with references to the mechanical and chemical behavior of thermally modified wood, including the work of Yildiz et al. 2006, on spruce wood modified by heat. The Weyerhaeuser Company, 2023, is also mentioned as a relevant industry player.